Hello everyone, my name is Michael Reitzenstein and I am a full-stack Clojure developer at Bookwell, a startup in Melbourne, Australia. And we are actually hiring, so if you don't mind a bit of a commute, see me after the show. What I'm presenting today is a compiler that takes Clojure code and translates it into C, taking advantage of Clojure 1.9's new spec and generator features in order to strip away abstractions and boilerplate. The resulting code respects Clojure's semantics, but it elides the work required to do it where possible, running it at compile time rather than at runtime. And this means that it looks a lot more like something that you would write in hand in C. So why compilers? Why am I interested in compilers? In short, the death of Moore's law. Low-budget hardware design is sort of catching up to the blazing edge as the blazing edge is moving more slowly. Graphics card companies even skipped a process node recently, which is unprecedented. And consequently, we're now experiencing a bit of a renaissance in novel hardware architecture. For example, Xeon Phi, FPGAs in the data center, like Microsoft is doing, chips with dozens of low-power ARM cores, and even exotic tech like Adaptiva's new 1000-core processor and CPUs stacked on top of memory. And of course, the elephant in the room, GPU computing, is so common now that 5 out of 45 of the available EC2 instance types feature graphics processors. Now, I would assert that this would not have happened if x86 scaling had kept the pace that it set in the 90s and early 2000s. You need to be an order of magnitude better with your hardware before people are going to port their programs over to use your system. And when your competition is itself doubling in performance every 18 months, it's not going to happen. A short delay means you're no longer better enough to warrant the porting process. A big delay means you're no longer better at all. And if you don't believe me, look at what happened to Intel's own Itanium processors. I actually blanked on the name for a bit until I remembered that people used to call it the Itanic, which is sort of a 2-for-1 indication of just how that went. But we need to be able to program these novel architectures without rewriting all of our code, or they're still not going to get made because they won't get mainstream adoption. And that means a next generation of compilers. The performance trade-offs for these systems is extremely complicated, and the methods used to program them often boils down not to analysis, but modify my program, benchmark it, and repeat in a loop, a sort of human-powered genetic search process. If we even need to manually hold our compiler's hand when dealing with non-uniform memory architectures, what hope do we have of breaking down complicated programs and scheduling them to be run across 1,000 cores, each of which has slightly different communication characteristics? And why Clojure? A large subset of the language maintains immutable semantics with referential transparency. This means that you can cache results, rerun code, remove code if it's not needed, and swap it out anywhere you'd like to, without having to worry about mutability. It also provides a powerful set of abstractions that can be feasibly elided or optimized down for sections of code. And I think it could even go a bit further. For instance, what about first-class spec-based dispatch? It's a possibility. Clojure's homoiconicity also allows for easy code rewriting. And indeed, the intermediate language of my compiler remains valid Clojure code right until the point at which it is translated to C. For instance, an unboxed native integer is represented by a hash map like this. And if you're paying attention, yes, that is an unboxed int being represented by a boxed int. The aims for the project. I aim to compile purely functional numeric Clojure by rewriting, inlining, moving, simplifying, and specializing code. Constructs such as clojures, that's a clojure is in, not closure, the clojure is in the capturing of variables. Hash maps and multi-dispatch should be elided where possible, or replaced by a simplified construct that performs the same job, but these constructs should still be supported in full when required. I also aim to build tooling which will prove useful for testing Clojure code in general. Testing optimizations, after all, is just a subset of just testing code in general, so more on that later. What is not a name for this project? Primarily supporting mutability. As mentioned before, the compiler relies heavily on referential transparency, and it makes things just so much easier. Because of this, the input programs must always be purely functional, although the compiler itself is free to reintroduce mutability as it would like to as an optimization. For instance, with caching, like a simple Memoize is actually mutability. It's updating an object somewhere. I'm also not planning to support interop with Java and other platforms. Basically because the main reason is referential transparency needs to be maintained. And so if you are using plus, that's fine because you can call it as many times as you'd like to. But if you're calling write a file, the compiler is not free to call that function twice. It's not free to not call it at all. And so it's not possible to support that with this system. So without some prerequisite knowledge on spec and gen, this talk is just going to be gibberish. So I'm just going to go a quick overview, just a few minutes. Although I suspect most of you are sort of up to date. So it's a new data validation and generation framework being added to Clojure 1.9, and it's sort of becoming a key part of the overall Clojure solution. It's sort of answer to static typing. Any predicate that in existing Clojure code can act as a spec. For instance, integer, float. You call valid on it, which checks if a value is valid according to the spec, and it just works, including arbitrary user functions. There's sort of no code behind the scenes in order to check a spec of a predicate. Specs can be arbitrarily combined. For instance, this is a tuple of integer and float, and then that will match if we pass it an integer and a float, and it won't match if we pass it an integer and an integer. Generators sort of perform the reverse function, where they take a spec and then they output data that conforms to the spec. It even works on compounds, like our example before of tuple integer float. It can generate that without problem. Or down the bottom where I've got ranged int, which is an integer between 0 and 5, you can also generate that. Now, the generators themselves aren't magic. You actually have to specify how to generate for your custom predicates. This isn't the syntax that you'd use, but I just wanted to condense it down for the slides. So, it's actually pretty easy to convert most Clojure code to C if you don't care at all about performance. Firstly, you define a boxed data type, which can contain, for example, float, int, or a linked list element. Then you simply stub out re-implementations of the core Clojure functions, such as count, conj, map, filter, that operate on these data types. And then your code can be mechanically translated. And the hardest part is literally generating correct C syntax and supporting closures. But Clojure is a highly dynamic language. For example, simply to add two numbers together, various forms of abstraction are involved. Plus itself takes a variable number of arguments. And the arguments can be of type float, int, etc. And they can be mixed, requiring a numeric tower which converts between them at runtime. Even truthiness itself has specific semantics. In Clojure, it's and, not nil, not false. But Clojure is not a slow language, and if it's doing that much work, why is that? On all three of its commonly used platforms, the JVM, .NET, and JavaScript, the various JavaScript platforms, it's really standing on the shoulders of giants. The JIT compilers provided by these platforms are extremely fast. They monitor the execution of the program in real time with real data flowing through it, and then optimize the code for the usage patterns that you're actually experiencing at runtime. And if you've ever been frustrated by a task that you're working on, spare a thought for the engineers of those JITs. They take unoptimized code that is currently running and hot swap in an optimized version on stack. Then, when there's an error in the optimized code, they determine where it would have happened in the de-optimized code and then pretend that it happened there instead to give you your stack traces, etc. It's honestly a miracle that this stuff works at all. And this is an example of some Clojure boilerplate functions written in C. So we've got first and conj, and obj is a struct which holds the boxed data types. So the compiler's method is to analyzing Clojure code statically in order to make inferences about its behavior is very complicated. But it's not difficult at all to analyze Clojure code that's running, as you would do in a JIT. But we have Clojure.Spec generators, and we can generate sample data which we can feed through our program ahead of time, observing the execution of our program. Furthermore, if we treat the behavior of the program under this generated data as exhaustive, we can perform significant inlining and elide any paths not taken. Now, this differs from a standard JIT compiler, which builds in guards, so if the program data under execution changes, the behavior remains correct, the performance just suffers. However, in the pursuit of high-end performance, the more extreme approach is required. The nice thing about immutability is we can actually bail out of the execution of our code and de-optimize at any time. Unlike the de-optimization performed by a standard JIT during execution, where it's got to perform all this bookkeeping to reconcile the two versions of the code, with a system like this, you can just bail out as far as you'd like and then rerun the code. It doesn't matter if you run it twice. It's all immutable. And if we find an error in our optimization, we can actually run an optimized version of the code side by side with a de-optimized version of the code, and then strip away the optimizations until we actually find the place at which the error creeps in. And because we're running the compilation ahead of time, we can afford to take significantly longer amount of time analyzing the functions. It's all immutable data as well. You're optimizing a piece of code against a spec, both of which are immutable, and that means that you can cache the results indefinitely. So even though the performance is slow, you don't pay that penalty over and over and over again. So let's take an example, a closer look at adding two numbers together. This is the source code for a re-implementation of plus that takes a variable number of arguments. And you can see here that in the case statement, it is branching depending on the number of arguments that you're passing to plus. Of course, if you call plus without any arguments, it just returns 0. If you call it with one argument, it just returns that argument. And 2, then it will perform the plus. And then more than 2, it will recursively call itself. It will recursively call itself and then call the internal plus on the results. Now, this is the numeric tower, which is the version of plus that operates on just 2 arguments. Now, I've sort of left off whole sections because in order to just support a float and an integer, it would be 4 times longer than this, and it's just too long for the slide. And so this is a single-story numeric tower, which I don't actually think is a thing, but you probably get the idea of how it works. So let's try optimizing this code. So we're optimizing plus, where the args that we're passing in is a tuple of integer and integer. The first thing you'll notice is that count args, no matter what data is generated and passed in, is always going to be 2. And so we can actually replace count args in the function body with just the constant. And then furthermore, because case 2 it's always going to return the branch of 2, the case is now a constant, we can actually strip away the rest of the case statement, just leaving the branch that deals with 2. And so our plus has been simplified, it's been specialized to handle the case of passing in 2 arguments only. Now let's look at the numeric tower, which is being called by our plus, and A is an integer and B is an integer. Now, of course, there's only one branch here, and so it's a bit silly to do this, but the same principle would apply if you had a full numeric tower with lots of branches. But essentially, integer A, the call to integer A and the call to integer B will always return true, no matter what data is generated. And so we just replace those function calls with the constants, and then we propagate it through, and of course, con true is always going to return that branch, as opposed to nil. And so we're just stripping away the code, and then we inline +2 into our original plus to get this. And what this does is it simply explicitly gets the first of the array of arguments, unboxes it. It gets the second of the array of arguments, unboxes that. It calls native plus int on it, which is sort of our native plus. In C, that would just be plus. And then it boxes the integer again after it's been calculated in order to become a Clojure value again. So we'd also like to specialize the fact that it only takes 2 arguments. We can actually transform the code to take explicit arguments because we know it's only 2. And to do this, we replace args, the variable arguments, with just 2 parameters, and then recreate our arguments in the body of the code. So we've got first xy and second xy, and then simple pattern matching will elide that. And then there we have it. It's essentially an almost a native plus function. Oop. So that's how the process works, but let's take a look at it, exactly how it happens in the compiler itself. So there are a few more parts to it, and this is a bit more of a complete implementation. We've got plus, +2, and an implementation of truthy for Clojure. Clojure's version of truthiness. And we can actually optimize by sliding this slider to see the various stages of optimization that take place. Now this is actually optimizing, to make it a bit more interesting, this is optimizing it to 3 arguments called to plus. And the reason for that is just so that the recursion of plus into itself takes place. And we can see that it's elided as well. And so first we see that the, okay, this is, it might be a bit difficult to read, and so don't pay too close of attention. I'm going to speed through it. But essentially, we specialize the code, simplify it, and then inline in a few passes, which at the start makes it a lot longer, and then as it's simplified, it gets cleaned up. Until we get to this, which is similar to what I showed you before, except it handles 3 arguments, not 2. And then we take the step of explicitly defining our arguments. And then the last step is to unbox those arguments. And so instead of taking a Clojure integer, or 3 Clojure integers, and then returning a Clojure integer, we're actually going to take a unboxed integer and return an unboxed integer. And all that involves is stripping away the boxes, essentially. And so this is a version of Clojure's plus that takes 3 integers and returns an integer, and it operates entirely on native objects. So let's take a look at the C output of the compiler. Now, this is the naive way of adding 3 numbers in Clojure. When translated to C, this is what it takes. Clojure's compiler isn't that bad. I mean, it does some optimizations of its own, clearly, because the program's run. But this is about 1,000 times slower than just adding 2 numbers in C. But it works. It works fine. At each stage of the optimization, it actually, the C code that is defined here, it runs. It's always going to run. The question is how quickly. And so we're performing the same optimizations on the code with the same slider. And so you can kind of get a picture of the other side of it. You can see when it inlines there, it's just a mass of code, but then it gets specialized away with the same process. And then we end up with the same result that we had in the Clojure side. This is the C side, where it's taking a list of arguments, it's extracting the first 3 arguments from the list, even though we know it's a list. It's not built that way. It unboxes them, adds them together with C's native addition function, which is just the plus sign, and then we make an integer out of it. Now, we can also perform the explicit arguments pass that we did before, in which case we're just passing in 3 Clojure objects. We unbox them, add them, and make a new integer. And then when we do the unboxing pass onto it, then we just have exactly what you would have written in C. But it's important to note that this process respects Clojure's semantics. If Clojure's truthiness, instead of and, not nil, not false, were instead, for some crazy reason, and, not nil, not false, not 7, that would still be respected in this output process. I suspect that the result would be the same, but if it were not, this code would actually be different. Clojure's semantics are in fact being run at compile time, not at runtime, and that is what gives us our speed. So far, I haven't really showed you anything that you couldn't do with a static compiler easily. But where things get interesting is sort of the higher order optimizations. So let's just take the naive implementation of the Fibonacci sequence. I think you're all pretty familiar with it. And of course, it runs in exponential time, which is it's a lot, because if you run fib 100 on the command line, it will never get there. But then you run fib 10 and it's nearly instantaneous. Now, the traditional way to optimize Fibonacci is, of course, to memoize it, just like so. So it's exactly the same function body. The only difference is that Memoize will remember the result to each call of Fibonacci, and so they're not repeated, and it just returns the value from cache when it exists. And that transforms the algorithm into a linear time, which is obviously a very big jump. But there's an interesting property of the Fibonacci sequence. So say we're passing an integer that we know to be at least equal to 5, and we specialize our function to that. The first thing we can notice is that this branch of is n less than 2, well, we know that's not true, so we can strip away that branch entirely. It becomes false, and then it's stripped away. But then we can actually inline the next level of the Fibonacci sequence. So fib take n1, we can actually take the next level, the next call to Fibonacci, and inline it into our body, which becomes this, which we can then simplify to this. And so we've, in effect, we've skipped a level of the Fibonacci function. So we've skipped a level of the Fibonacci function, and so if you run this on code, one second. So obviously here we have to recurse into our original Fibonacci function for this optimization to remain valid, because eventually n is going to be equal to 0. But essentially we're skipping a level of the Fibonacci sequence, and there's no limit to how far you can take this optimization. The inlining can continue as long as your spec allows it. And so if you know that x is greater than 8, you can actually skip 8 levels down. If x is greater than 16, you can skip 16 levels down. If it's greater than 32, you can skip 32 levels down. And you can actually build a version of the Fibonacci function completely automatically by segmenting it into these little exponential boxes where we're going, is x greater than 8 or 16, etc. And then we build this. I'm a bit sorry about the wrapping. But essentially it's a version of the Fibonacci function that is now linear in time complexity, because when our value is large, it's skipping a lot of levels. And when it's smaller, obviously, it performs the same. It's now linear. So that's the same time complexity as Memoized, but we can actually combine the two optimizations. And so if we Memoize that new Fibonacci sequence, Fib is now O log n. And that is a completely automatic, generalizable optimization. There's nothing specific to Fibonacci about it. It'll be valid for some code. It'll be useful for some code, I should say. Most code, no. But if we can maintain a library of these sorts of optimizations, techniques that we can try on code, then we can test them all and essentially see. And that's not all, because obviously if we want to support Fibonacci, say we've got long, like arbitrary sized integers, our const statement is going to get very, very large. Obviously, each doubling of the value that we want to support is going to add a new branch to the const search. But we can even further than that turn the cond into a binary search in order to avoid the cost of that. So, dear audience, this is where I failed you. This was meant to be the part of the talk where I actually demo outputting to Java instead of C, and then using a dynamic class loader at runtime to run our optimized Fibonacci. But there were some technical issues, so you're just going to have to take my word for it that it works. I will release the open source version of it soon. But it is completely possible to perform the same optimization progress. It is completely possible to perform the same optimization process, output Java, and then run it in your REPL in real time. But it does take a little while to compile. So, can you build a production compiler like this? I've been doing it for 6 months. I've been working on this for 6 months, and I'm still not sure, to be perfectly honest. But I think at the very least, it's an interesting way to approach the problem. So one advantage of the technique is that it is so simple to do. If you've ever tried to do some optimization based on type inference or data flows, it is seriously difficult. With this, the process is just trivial to do. We can also elide abstractions that can't even run on the machine that we're targeting. For instance, if you would like to program GPU shaders, but you would like to program them as if they had hash maps, but in a sensible way so they can still be transformed into structs at runtime, you can do that. And you can even use, for instance, keys and zip map on them. Another advantage is that the work can be effectively memoized and that work shared. So how many times has Minecraft been recompiled? It must be in the billions, and it's performing the same work over and over and over again. But what if with each recompilation, instead of recompiling Minecraft, we added to the global body of knowledge of how to run Minecraft very quickly? I think that would be an interesting approach to take. And it also allows for building multiple specialized versions of the same code. You can perform some analysis of array processing And you can figure out that if it's greater than 1,000 elements long, it's beneficial to spawn some new threads to process it using multiple cores. But if it's short, then it's not beneficial. And so you can actually build both versions of that function at compile time and then dispatch them at runtime. So what are the disadvantages? So the compile times are really quite long. If you're doing, obviously, like I said before, you can Memoize the stages, but when you're doing new work, it does actually take quite some time. And the safer you want it to be, with are your specs going to generate the right values, the longer you have to run it. Plus takes about a minute to compile from scratch, and the Fibonacci sequence that I showed earlier, where it does the full optimizations and inlines into itself, takes about 15 minutes to compile to Java. So it is quite a lot of work. It's also difficult to optimize between pieces of the program. The ideal case is that you sort of section off chunks, purely functional chunks of a program, and then you optimize them individually. But if you want to sort of optimize between them, you sort of have to combine them into one big chunk and then run the optimizations over both of them at the same time. Although that said, you can actually perform some pretty nice optimizations between them, strip away a lot of code, and so it's a double-edged sword there. And of course, the elephant in the room is sort of the probabilistic nature of the compiler. The data generated by the specs needs to be exhaustive. If you've got a rare edge case that's never tripped, you could be in the dark until production, until your program behavior is incorrect. And there's sort of a trade-off between how deep you let your generated values run down into the program, because at some point you have to stop, infer the spec, and then regenerate new values in order to reach even further down, because otherwise you're just not going to get the program coverage that you otherwise would have had. And this loses potential relationships in the test data that the inference of the spec may not understand. But I sort of see three main ways to mitigate the probabilistic nature of it. So the first is fuzzing the program. If we take a Clojure compiler, a Clojure eval function that has hooks into it so it can actually analyze the code as it's written, we can take the initial generated data and mutate it genetically until it reaches all of the branches of the code. And where we see novelty in the program, when there's a new piece of input data that reaches a new part of the program, we can then further work on regenerating that input data to see if we can even explore further avenues. The second is a hybrid approach, which maintains the de-optimized paths, just like in a JIT, and it only aligns when a proper type checker proves that it's safe. But this would get rid of the ability to, for example, use hash maps and then target GPU shaders, for instance. And thirdly, maintaining a shared body of knowledge about our code. And to me, this is the most interesting one. We're performing all of this analysis on the code, and why can't we sort of keep this body of knowledge around that lists properties that are invariants of the code? For instance, if you pass in an integer to plus, it will return that same integer. If you pass in two integers to plus, it will return an integer. And if these properties are ever found to be violated, then we can share that knowledge to the central database. And this made me feel a bit better about the whole thing. Because each individual error made by the compiler, in theory, would only happen once. And it's sort of the scientific method, isn't it? So I think it's an interesting avenue to take. Any questions? It looks like we've got some time. Okay, so the question was, the specs are written by humans. Could you create a spec that causes the program to loop forever? I think the answer is yes. And of course, you've got the halting problem there, and that would be something to keep in mind. Any other questions? Could you talk up a bit? So the question is, when you modify plus to take unboxed integers, you also have to change the call site, and that's absolutely correct. That's part of the process, and it helps when you're calling a lot of code that is constantly boxing and unboxing integers. Essentially, the purpose of it is to just maintain your unboxed integers and get rid of the wasteful and unnecessary boxing and unboxing. Any other questions? Oh, that looks like it's about it. Thank you all.